This is my intermediate algebra course. Today we're going to review for the final test. This final test is going to be cumulative, meaning it's going to cover everything that we've learned in the entire course. You can use a calculator, and you don't have to write the Roman numerals for the exponent rules or logarithm rules that you use. And remember, don't leave your answers with fraction exponents, negative exponents, zero power exponents, or first power exponents. Now, this class might be a little long because we're doing a final exam that covers everything in the course. So if you want to take a break in between, that's fine. And as I've mentioned, I don't really care how long the final exam takes you in the next class, as long as you can do it without any help. So you might take an hour to finish the test. You might take 5 hours. I don't really care. If it gets too long, you can just take a break in between. As I've mentioned many times throughout this course, there are some subjects where you can study the night before and ace the exam. Well, math doesn't work that way. You need at least 2 or 3 days, maybe 4, to prepare for a test. But when it comes to a final test, you need even more time. You probably need 4, 5, 6 days, maybe a week to prepare for a final exam, because you're going to have to go back and make sure that you know everything. But it doesn't matter how many times you tell students to study for a test, they're not going to do it. So as usual, in order to force you to do at least some studying, we're going to do a practice final exam right now together, and I'm going to give you a practice final exam for homework. And these tests are going to force you to do some studying, but they're also going to familiarize you with the format of the final test. So that said, let's get started. As usual, I want you to attempt these problems on your own before just watching me do them, so you can get a feel for how ready you are for this test. So I want you to try problem number 1, and when you come back, we'll do it together. Okay, we're back. So we see that there's 2 3s here, and so that could be a problem, because if you plug in an input and then you get more than one output for that same input, the relation cannot represent a function. But this is kind of a trick problem, because when you plug in 3, you get 0 over here, but you get the same thing over here, so it's a trick. Turns out that this can be a function because we don't see any inputs that produce more than one output. Over here we have no repeated x values, so that can definitely be a function. And when we go to the graphs, we need to use the vertical line test. So let's draw vertical lines through this graph, and you can see that each vertical line only touches the red graph once, so that can be a function. But if we do the vertical line test over here, we see that there's all kinds of lines that will touch the graph more than once, which means that this graph cannot represent a function. So if you got that one right, good job. Now, again, be aware that this part here is kind of a trick, so don't get tricked by that. Okay, go ahead and try number 2, and when you come back, we'll do it together. All right, we're back. So we're going to use FOIL. We're going to multiply the first terms. I times 3i is 3i squared. And then the outside terms, I times negative 4 is negative 4i. And then the inside terms, 2 times 3i is 6i. And then the last terms, 2 times negative 4 is negative 8. So I squared is negative 1. So that green I squared became negative 1. And negative 4i plus 6i that becomes 2i, and we can just rewrite the negative 8. And I'm going to scrunch this in a little bit. 3 times negative 1 is negative 3, obviously. I'm just taking this step by step. You can skip some steps if you want. And negative 3 minus 8 is negative 11. And we just rewrite the 2i, so now we have that expression written in a plus bi form. So if you got that one right, excellent. Okay, try number 3. And when you come back, we'll do it together. All right, we're back. So what we need to do here is isolate the exponential expression. It's not isolated because the 8 and the 2 are next to it, so we need to get the 2 and the 8 on the other side of the equation. So I'm going to subtract 2 from both sides of the equation. And then I'm going to divide both sides of the equation by 8. And at this point, we're stuck. We can't do anything. Unless we know how to translate or transform the equation to a logarithmic equation. We cannot figure out what this is. E is 2.71 something something something. It's a very difficult equation to solve, so we need to use the calculator. And to do that, we have to translate to an exponential equation. So the exponent is equal to log base e of 3 over 8. This is what we tell the calculator. If you raise this special number to some power and you get 3/8, what is that yellow power? That's what we're looking for. So that's what we tell the calculator. But the calculator is difficult to use with this notation. So that in your calculator there's an abbreviation, ln. So we're going to use ln in the calculator. And now go ahead and get your calculator out. You can enter 3 and then divided by 8 equals. You should have 0.375 and then push the ln button. Now if you're using a graphing calculator, then you're probably going to push the ln button first. So just be aware of that. So 3x is equal to, well, it's approximately equal to negative 0.98082, and it just keeps going on and on and on. So then we're just going to divide that by 3, and we get x is approximately equal to negative 0.327. So I rounded off to the nearest thousandth place, because that's what it told us to do up here in purple. You see that? It says round to the nearest thousandth. All right, so if you got that one right, perfect. Go ahead and try number 4, and when you come back, we'll do it together. Okay, we're back. So we need to use exponent rule number 1 to add those exponents. So 6 plus 3 is 9. We need to use exponent rule number 7. Anything raised to the 0 power is just 1. And we can use exponent rule number 4 here. If you're raising a fraction to some power, then that is equal to the numerator of the fraction raised to that power divided by the denominator of the fraction raised to that same power. That's exponent rule number 4. Now we're going to use exponent rule number 5. When you raise a power to some power, you just multiply the exponents. So we get x to the 15th power over y to the 10th power. And when you're multiplying something by 1, obviously it doesn't change it, so that would just be x to the 9th. and then we multiply and we get x to the 24th over y to the 10th power. So if you got that one right, very good, perfect. Okay, on to number 5. And by the way, you should know by now when you're multiplying a fraction by what appears to be a whole number, you can just write that whole number as over 1. And then when you multiply fractions, you just multiply the denominators and the numerators, but you should know that by now, so I'm just reminding you. Okay, so now try number 5, and when you come back, we'll do it together. Okay, we're back. So this equation is too complicated. We need to simplify it. So what we need to do is we need to combine these logarithms, but the problem is we can't. We can't combine them because these purple numbers here are in the way. So we have to use logarithm property 7 to take that 2 and throw it up into, so it becomes the exponent of what's inside the log function. And we can do the same thing with this 3. We can throw it up so it becomes log base x of 2 to the 3rd power. Now we can simplify. We have log base x of 25 minus log base x of 8 is equal to 1. And now we can use logarithm property 6. That tells us if we're subtracting logarithms that have the same base, notice we have the same base. If you don't have the same base and both logarithms, then the property doesn't work. But logarithm property 6 tells us that we can combine and it becomes log base x of 25 over 8. When you're subtracting logarithms, you take the expressions inside and you divide them. If you're adding logarithms, you take the expressions inside and multiply them. So, do you agree that this equation here is much simpler than this orange equation up there? We've gone a long way to simplify this equation. Now, we're out of room, but don't panic. We can just use an arrow to go up here. There's really nothing that we can do at this point to solve this problem, unless we know how to translate to an exponential equation. This is a logarithmic equation. We need to transform it to an exponential equation. The base is always that little number, x. The exponent is always what the logarithm is equal to, because a logarithm is an exponent. And whatever's in the log function goes on the other side. So we just translated this logarithmic equation to an exponential equation. Anything raised to the first power is just whatever that number is, and you're done. X is equal to 25 over 8. This is exponent property 6. So if you got that one right, excellent. Go ahead and try number 6. Remember, you don't have to write the exponent rules, the Roman numerals of the exponent rules, or the Roman numerals of the logarithm properties either. Try number 6. When you come back, we'll do it together. Okay, we're back. So on the right side of the equation, I'm going to use exponent rule number 2, which tells us if we're dividing powers, we just subtract the exponents. So x minus 2x is negative x. And the only reason we can do that is because the bases are the same. If the bases were not the same, that wouldn't work. So I'm going to change 4 to 2 to the 2nd power. There's a couple different ways we could do this. We could use exponent rule 9 and then exponent rule number 5 and combine those, or we can do what I'm going to do. I'm going to use exponent rule number 10. That tells us that the expression on the left side is going to be 2 to the 2/3 power. Again, I used exponent rule number 10. Now I'm going to change 8 so that it's 2 to the third power. I'm not using an exponent rule. I'm just changing 8 so that it's 2 to the third power. Now I'm going to use exponent rule number 5, which tells us that if we raise a power to another power, we just multiply the exponents. So 3 times negative x is negative 3x. And now we're at that critical stage where we have exponential expressions that are equal to each other and the bases are the same. So what does that mean? Well, it means obviously the exponents must be equal. That's the only way the equation could possibly be true. So now we divide both sides by negative 3 and we get negative 2 over 9 is equal to x. So if you got that one right, good job. Okay, go ahead and try number 7, and when you come back, we'll do it together. Okay, we're back. So now we're going to use exponent rule 3 going in the reverse direction. So that becomes 3 times 4 raised to the x power. That might be kind of confusing, but it's confusing because we're going in the reverse direction. I'm going to change 144 to 12 to the second power. I'm going to multiply 3 and 4 to get 12 to the x power. And I'm going to use exponent rule number 5. When you raise a power to another power, you multiply the exponents. So that becomes 2x minus 2. So now I'm going to use exponent rule number 8 going in the reverse direction. So now we have 12 to the negative 2x minus 2. So we're just changing the sign. If you start with a negative exponent, then you go down into the denominator, it becomes a fraction, but we're just going in the reverse direction, so we have to make it a negative. So now I'm just going to use the distribution property. Negative 1 times 2x is negative x, and negative 1 times negative 2 is positive 2. So again, we're at that critical point where we have exponential expressions that are equal to each other and the bases are the same, which means the only way that that equation could possibly work is if the exponents were equal. Now I'm going to add 2x to both sides and divide both sides by 3, and we get 2 thirds. So if you got that one right, excellent. Okay, go ahead and try number 8, and when you come back, we'll do it together. All right, we're back. So when you're trying to find the equation of a parabola, remember it's convenient to use the vertex form of a parabola. And we're told that we have a point negative 1, or it's negative 2, 1. So the y value is 1. A we don't know. The x value of the point is negative 2. And the x value of the vertex is 2. And the y value of the vertex is 10. So we can use all that information to help us find the constant a that we're looking for. Once we find a, we'll be done with the problem. So then we get a times 16. Subtract 10 from both sides and we get negative 9 is equal to 16a. Divide both sides by 16 and we get negative 9 over 16. And our final answer, our final equation is going to be y is equal to negative 9 over 16 times x minus 2 squared plus 10. So if you got that right, good job. Okay. On to number 9. Number 9 is kind of a big problem. So if you'd like, you can just do the first part and wait for us to do the second part together. Go ahead and try number 9. When you come back, we'll do it together. Okay, we're back. So we're going to find f over g of 1. Well, what does that mean? It means plug in 1 to f and then divide that value by g with 1 plugged in. That's just what f over g means. F of 1 is natural log with 1 plugged in, and g of 1 is the absolute value of 1 plus 3. Alright, so at this point, you might get kind of stuck there. What in the world is natural log 1? Well, that's log base e of 1. Remember, we learned that whenever you plug in 1 to any kind of logarithm, you always get 0. The answer is always 0. Now, why is that? Because if you make that an equation, x is equal to log base e of 1, and then you translate to an exponential equation, the base is e, the exponent is always what the logarithm is equal to, and whatever's in the log function goes on the other side. So you can see that the only way that this equation would work is if x were 0. So x, which is the log base e of 1 expression that we're looking for, x must be equal to 0. Whenever you plug in 1 to a logarithm, you always get 0. So we have 0 over the absolute value of 4, which is just 4. And of course, 0 divided by 4 is just 0. So if you got that right, perfect. If you got a little confused by natural log 1, that's okay, but now you know. Okay. So this is a composite function. What it means is that we're plugging in g of x into f of x. So let's do this step by step. There's a lot of different ways to do this, but let's plug in g of x first. G of x is the absolute value of x plus 3. Am I right about that? G of x is the absolute value of x plus 3. So I'm plugging that into the f function. So what does that mean? What it means is you have f up here. You have the input x in f, natural log x. I'm actually going to plug in that yellow g of x into that f function. So that can be kind of confusing, but that's it. We're done. So it may look really complicated, but it's really not that difficult at all. Okay. Find the values below if h of x equals that function there. So this is what's called a piecewise function. H of 11. If x is 11, then what is the output h? So we have to figure out what equation we're going to use. Do we use the top equation or do we use the bottom equation? Well, in order to figure that out, you have to look at these bounds here, if you will. You use this equation when you go from -6 to -2, or your x value is between those numbers. And if your x value is equal to -2 or less than 10, between -2 and 10 and including -2, then you use the equation below. But 11 is not in those regions. So what that means is the function is not even defined if x is 11. So the answer is undefined. If you got that right, good. Now we're going to plug in -2. Well, -2 is here, but do we use the top equation or the bottom equation? Well, up here it says x has to be less than 2, but down here it says -2 is less than or equal to x. So that means if your x value is -2, we're going to use the bottom equation. So plug in -2 to that x cubed function, and we get -8. So have you got that answer? Excellent. Now we're going to plug in 3. That's in this region here. So we use the bottom equation. So we have 3 cubed, which is 27. And plug in -5. -5 is in this interval here. So we're going to plug in -5 to that equation. So we get 8 times -5 minus 2, which is -40, minus 2, which is -42. Okay. So if you got those right, good job. Now we're going to write the domain of h. The domain of this piecewise function is determined by the intervals here, the bounds. So the domain, which is all the possible x values, and it tells us to use interval notation. So these intervals are connected, which means that we can say the domain is simply -6 to 10, but not including -6 or 10. So everything between -6 and 10. Next problem, it says write the domain of h in set notation. So the domain is the set of all x values such that x has to be between -6 and 10. So if you got that one right, good job. All right. Go ahead and try number 10. And when you come back, we'll do it together. Okay, we're back. So we're first going to isolate the absolute value expression. It's not isolated right now because the -3 and the 2 are next to it. So I'm going to subtract 2 from both sides of the inequality. And one of the biggest mistakes that you see students make is they somehow get rid of that negative symbol there. Well, that negative goes with the 3. It has nothing to do with the 2. So then I'm going to divide both sides of the inequality by -3. And remember, when you divide both sides of an inequality by a negative, or if you multiply both sides of an inequality by a negative, then you have to flip the inequality symbol. Okay. So now the absolute value is less than some number. Now let's go over the possibilities. If the absolute value were less than a negative number, then that would mean that there's no solution. That's impossible, because the absolute value happens to be positive, so there's no way it could be less than a negative number. If the absolute value were greater than a negative number, then the answer would be all real numbers. There's an infinite number of solutions, because it doesn't matter what you plug into the absolute value, it's always going to be bigger than a negative number. So there's a lot of different options here, and those are just a couple that we could discuss. But in this case, we have an absolute value that's less than a positive number. So you need to memorize the options. If it's greater than a positive number, then it's something different. If it's greater than, you would use an or. If it's less than, then you use an and. So x/4 plus 1 is less than 2, and x/4 plus 1 is greater than -2. How do I know that? Well, I have it memorized. From years and years and years of doing this, I just know that's what it's going to be. Now, if you forget if it's or if it's and you forget which way the inequality symbol should be going, you can actually figure it out by solving the inequality. So let's subtract 1 from both sides and multiply by 4, and we get x is less than 4. And again, subtract 1 from both sides of the inequality, multiply by 4, and we get x is greater than negative 12. So that is the possible algebraic solution if we did it correctly. But in order to check and make sure you did it correctly, we're going to write a number line, and we want open dots because these inequality symbols are not equal to symbols, they're just less than symbols. If you have a less than or equal to symbol, then you need to fill in that dot. So now, if we choose a point, say let's choose 0. 0 is between, because there's two possible options. The answers can be here, or the answers can be on the outsides. That's typically the two options you're going to see. Now there are other possibilities, but those are the two that we're considering. If you plug in 0, which is in this region here, to the original inequality, you see that it works. 0 divided by 4 is 0, plus 1, absolute value of 1 is 1, 1 times negative 3 is negative 3, negative 3 plus 2 is negative 1. Negative 1 is greater than negative 4. So that means that our answer is correct. It's x is less than 4 and x is greater than negative 12. So this is the graphical solution. So if your inequalities were not correct, you could just go back and change those based on checking your graphical solution there. Okay. On to number 11. Go ahead and try number 11. When you come back, we'll do it together. Okay, we're back. So we are going to use logarithm rule number 5 to combine these logarithms because the equation is just too complicated. And the only reason we can do this is because all these green bases are the same. Well, we don't really care about the base on the left side of the equation at this point. So when you do that, you multiply what's inside the logarithms. And we can use the distribution rule. X times x minus 9 is x squared minus 9x. So now we have a logarithm that's equal to another logarithm. And the bases of the logarithms are the same. So what that means is that the inside of the logarithms have to be equal, or else there's no way the equation could possibly be true. Now we have a special equation. You need to recognize what type of equation this is, because there are special methods to solve this particular equation, and if you don't recognize it as that special equation, you're certainly not going to know the special methods to solve it. This is a quadratic equation, so we need to use the special methods associated with quadratic equations. But even though we recognize it as a quadratic equation and we know that we have to use special methods, we still can't solve this unless we put it in standard form. So I'm going to put everything on the right side of the equation. You could put everything on the left side, but then you'd end up with a negative x squared, and that's much more difficult to work with. So now I'm going to attempt to factor this. I don't know if it can be factored, but we'd prefer to factor it if we can. What two numbers multiply to get negative 10? If you multiply two numbers together, you get negative 10. But if you add those same numbers, you get negative 9. So what do you think? What would that be? If you said negative 10 and positive 1, you're correct. So what does this tell us? It tells us that one solution is 10 and another possible solution is -1. The problem is, if you plug in -1 into this logarithm, you can see that we have a negative in the logarithm, and that's not allowed. So that's called an extraneous solution. If you plug in 10, that'll work. That'll be okay. So 10 is a solution to the equation. So if you got that one right, excellent. And by the way, the reason that 10 is a solution is because if you plug it in here, 10 minus 10 is 0. 0 times 11 is 0. This is 11 because if you plug in 10 there, 10 plus 1 is 11. Okay. On to number 12. Number 12 is going to be a little challenging, a little more challenging than the problems we've done so far. You're going to have an extraneous solution. You got to figure out which one of those solutions is extraneous using logic. And remember, if you have a root, for example, root 5, well, you know root 5 is going to be between root 9 and root 4, right? So you may not know the exact value of root 5, but you know at least it's between 2 and 3. Not only do you know it's between 2 and 3, but you know it's going to be closer to 2. So you can use that logic to estimate, because root 5 is a lot closer to root 4 than it is to root 9. Okay, so go ahead and try number 12, and when you come back, we'll do it together. Okay, we're back, so we need to isolate this logarithmic expression. But before we do that, I would like to figure out what the base is. What is the base of the logarithm? The base is always this small little number here. The problem is there is no number there. So what is the base? Well, remember, when there's no number there, the base is always 10. So log base 10. So all I did was just rewrite everything, except I'm showing us what the base is. Now I'm going to subtract 2 from both sides, and you can do more than one algebraic step at once, but I'm just doing this step by step so you can see what's going on here. And now I'm going to divide both sides of the equation by -9. So then we get log base 10 of 2 minus x over 4x squared is equal to 0. Now we need to translate to an exponential equation because we're pretty much stuck at this point. We don't know what to do unless we translate to an exponential equation. So the base of the exponential equation is always 10. The exponent is always what the logarithm is equal to, and whatever's in the log function always goes on the other side of the equation. That's just the definition that mathematicians have given when it comes to that log notation. Now, exponent rule 7 tells us that anything raised to the 0 power is just 1. And by the way, I'm going to color code this stuff. So now we have an equation with a fraction, and the easiest way to deal with that is just to multiply both sides of the fraction by the denominator of the fraction. Students really don't like fractions. They get in the way. Students get really confused about how to solve them. But we're just going to multiply both sides of the fraction by 4x squared. And that's going to cancel out these two numbers here, or those two expressions. So we get 4x squared is equal to 2 minus x. Well, now we've got a situation, because again, this is a quadratic equation. it requires special methods, but if you don't recognize it as a quadratic equation, then you have no hope of using those special methods because you don't even recognize what it is. Furthermore, even if we recognize this as a quadratic equation and we know the tools that we need to solve the quadratic equation, we still cannot solve it because it's not in standard form. So let's put everything on the left side of the equation. And now it's in standard form. So now we can try to solve that. It looks like we're going to need the quadratic equation. If you try to factor that, you're going to see that it's not easily factored. So I'm going to rewrite up here. I just rewrote that exact same equation. And I'm going to use the quadratic formula. Now, you don't have to write the actual formula out on the test, but I'm just going to do this for educational purposes, just so to remind you of that formula. So B is 1. A is 4, and C is -2. So just to be clear, well, I think you have the point. So x is equal to -1 plus or minus root 1 squared is 1. -4 times 4 is -16 times -2 is +32. 2 times 4 is 8. So now we have x is equal to -1 plus or minus root 33 over 8. So we have two solutions to this equation. Now here's the part that gets a little difficult. Notice that the warning up here, we may have extraneous solutions. When it says beware of extraneous solutions, what it means is you're going to have some extraneous solutions. So there's two possible answers, just to be clear. X can be equal to -1 plus root 33 over 8, or it can be equal to -1 minus root 33 over 8. So we don't know which one is going to be an extraneous solution. All we know is that you can't have a negative inside a logarithm. When you subtract x from 2 and then divide by 4 times x squared, that red number that results cannot be negative. That's all we know. Now, we don't really care about the denominator because the denominator is squared. So if x ends up being negative, the denominator is really not going to affect much. We just want to know if you subtract a negative here, what's going to happen. Or if you subtract, x, whether it be negative or positive, what's going to happen. So root 33, I don't know exactly what that's going to be, but I know it's between root 36 and root 25. So root 25 is 5 and root 36 is 6. Now 33 is closer to 36, so I'm going to say it's about 5.7. I'm going to estimate root 33 to be approximately 5.7. So now let's think this through. If this is 5.7 approximately, and you add it to -1, you get 4.7. 4.7 divided by 8 is going to be about 1/2. So if you subtract 1/2 from 2, you're going to get a positive number. And of course, if you divide by x squared, that's going to be positive. So that solution works. that is definitely one of our solutions. And as you can imagine, it looks like the other solution is not going to work. Actually, it might work. We'll see. In fact, I think it actually is going to work. So, again, root 33 is approximately 5.7. So, negative 1 minus 5.7 is negative 6.7. Divide by 8, and that would be approximately negative 3/4. So if you subtract negative 3/4, well, that's a double negative. That becomes a positive. So actually, that's going to work also. So it turns out, in this case, I was wrong. Both answers work. But the moral of the story is that you have to check. You can't just assume. So that was kind of a trick problem. Both of those are solutions. So if you got that one right, good job. That was a more challenging problem. Okay, on to number 13. See if you can do number 13, and when you come back, we'll do it together. Okay, we're back. So, I don't know how multiplying 3 times root x is going to affect the graph, so I'm going to change the form of that equation. And I'm going to first change f of x to y, and then I'm going to divide both sides by 3. So when I do that, I get the equation y over 3 is equal to root x. So this is going to help me graph, and I'm going to write the parent graph. I'm going to graph that. So if you have your parent graph memorized, you should have your parent graph memorized. It's going to look like this. Then I'm going to graph y over 3 is equal to root x. So when you divide y by 3, you take all the x values and you multiply them by 3. So then you get this graph. So it's the same graph, you're just multiplying all the x values by 3. Excuse me, multiplying all the y values by 3. So if you got that one right, good job. We still have more to go, though. That's only part 1 of the problem. So now we have to find the domain and the range, but the domain and the range are going to be really easy because we have this graph. And so we can see just by looking at this graph, because this graph is the graph of this original function. It's just the equation is written in a different form. We can see the domain, all the x values. It's the set of all x values such that x is greater than or equal to 0. So that means all of these x values here. The range is the set of all y values such that y is greater than or equal to 0. Because y can be 0 or anything above 0. We can see just by looking at the graph what the domain and range are. So if you got that one right, good job. There were 2 parts to that problem. The first part was to find the graph using the transformations, and I'm going to require you to write these equations here on the test, so be sure to write the equations as well as the graphs. Okay, try number 14, and when you come back, we'll do it together. Okay, we're back. So this is in vertex form. So we can see the vertex immediately. And maybe I'll just write the form. That's a vertex form there, just so I can remind you what that is. A is obviously equal to 1/2. H is obviously equal to -4. And K is equal to 1. So to find the vertex, we learned that the vertex is just H comma K. So the vertex is -4, +1. Sorry, my computer's going kind of slow. There we go. -4, +1. So we can go ahead and graph that. 1, 2, 3, 4, +1. So that's about there. And the problem tells us to find the y-intercept. So if we let x be 0, 0 plus 4 is 4. 4 squared is 16. 16 times 1/2 is 8, and then 8 plus 1 is 9. So the y-intercept is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we can use symmetry to go across. 1, 2, 3, 4. 1, 2, 3, 4. That gives us another point. And maybe we can plug in another point. Maybe we'll plug in -2. And -2 plus 4 is 2. 2 squared is 4. 4 times 1/2 is 2. 2 plus 1 is 3. So we can use symmetry again to find some more points. And I don't really require you to find many other points. You can use, really you only have to find enough points to get a general idea of the shape of the graph. So we need the x-intercepts. Now this is kind of a trick problem because, as you can see, there are no x-intercepts. So we can say no x-intercepts. That's part of the answer. The y-intercept is 0, 9. I guess we don't really have to label it. And the vertex is -4, 1. And I think that's it. Oh wait, we have to draw the line of symmetry. So let's draw the line of symmetry. And we're also going to write its equation. It's very important to follow the directions of the test because you might end up finding something you don't need to find, or you may forget to write something that you were asked to write. The equation of the line of symmetry is x is equal to -4. And I guess I'll write that down here. You can write it on the graph, or you can write it down here. It's fine. I don't really specify. You're going to be pretty busy doing a lot of things with this test, so I don't require you to write the answer more than once. You can choose to write the answers on the graph or on paper or on both, but you only have to write the answer once. Okay, if you got that right, good job. On to number 15. Go ahead and try 15. When you come back, we'll do it together. All right, we're back. So it says to find the x-intercepts. We can easily find the x-intercepts. They're just 1 and -3. how was I able to find the x-intercept so quickly? Well, the reason is this is in intercept form. It's called intercept form because you can see the intercepts immediately. But just to refresh your memory, I'm going to write the general form. And, whoops, I wrote an equal sign there for some reason. A is equal to -2. M is equal to 1. And N is equal to -3. So, to find the vertex, or the x value of the vertex, we just use this formula m plus n over 2. M is 1 and n is -3. 1 plus -3 is -2. And -2 divided by 2 is -1. So the x value of the vertex is -1. So now let's find the y value of the vertex. To do that, we use the original equation, and we get -2 times -1. We're plugging in -1 into the equation, minus 1 times -1 again, plus 3. So we get -2 times -2 times +2, which is 8. So the coordinates of the vertex are -1, +8. -1, 1, 2, 3, 4, whoops, it should be +8. 1, 2, 3, 4, 5, 6, 7, 8. So that's the vertex there. Now you can try to get more accurate by plotting some more points if you want. The y-intercept is 6. We can use symmetry. You might try to plug in 2, but that'll probably be out of the window. X equals 2, that is. Actually, it looks like it might be in the window. So I plugged in 2. We can now use symmetry. So now we're ready to connect the dots. You don't have to draw so many points if you don't want to, but I'm just trying to be as accurate as possible. So we have the vertex. We found the vertex. And we found the x-intercepts. Let's write those x-intercepts. 1, 0, and -3, 0. And they want the focus in this problem. We need to find the focus. Or the coordinates of the focus. So remember, the coordinates of the focus are Vx, Vy plus P. But we can't find the y value of the focus because we don't have P. So first we have to find P. P is 1 over 4a. Maybe I should do this down here. So A is -2. So P is -1/8. Now that we have P, we can find the coordinates of the focus. The x value of the focus is always the x value of the vertex, so that's -1. The y value of the focus is always the y value of the vertex plus P, which is negative 1/8. So the coordinates of the focus are negative 1, comma, 7 and 7/8. So if you got that one right, excellent. You know, I'm going to require you to show those points on the graphs. So make sure you have dots for the x-intercepts and the vertex. And the focus is negative 1, 7 7/8. So that would be pretty close to the vertex, as it usually is. I'll just say that's a V for vertex. Or excuse me, F for focus. And the vertex obviously is here. Okay, if you got that one right, good job. Go ahead and try number 16, and when you come back, we'll do it together. Okay, we're back. So I'm going to first change f of x to y, just so it's easier for us to see what's happening here. Well, it's easier for us to just change the form of the equation. Then I'm going to add 3 to both sides. Then I'm going to divide both sides by negative 1, and I'm not going to distribute. I'm just going to keep the y outside of the sum. Now you could multiply y, that'd be fine, but I'm just going to keep it out. So let's see here. Okay, now let's graph the parent relation. That's the old familiar V. Now let's, the big question is, can we translate first or do we have to reflect first? And the answer is we have to reflect. Why is that? It's because if you add 3 to y first, then in the second step you're going to have to write a negative on y plus 3. But the transformation properties don't tell us what to do in that situation. They only tell us what to do when you write a negative on y, not y plus 3. So when we write a negative on y, we reflect across the x-axis, so I'm going to flip that graph down. And then I'm going to add 3 to y, and I'm going to add 3 to x. So that translates that graph 3 units to the left and 3 units down. So this is our new graph. And so we have negative y plus 3 is equal to absolute value of x plus 3. So the domain can be any value. The x values can be anything because the graph goes to the right forever, to the left forever. There's no gaps horizontally. So the domain is negative infinity to infinity. The range is going to have some restrictions because there's no points up here. So the range is negative infinity to negative 3, and we're going to include negative 3. Because that point at the very top of the V, that does have a y value of negative 3. And remember, you always have to start with what is perceived to be the lesser numbers. Goes lesser, smaller numbers to greater numbers, left to right. If you write negative 3 first in your interval notation, then that's incorrect. So if you got that one right, good job. on to number 17. Go ahead and attempt number 17. When you come back, we'll do it together. Okay, we're back. So this equation is in standard form. Now you don't have to write the standard form as I'm doing now, but I just want to remind you what that standard form looks like. And when you're in standard form, the x value of the vertex is equal to negative b over 2a. And b is negative 6, and a is 1. Simplify that, and we get 3. So, to find the y value of the vertex, we just plug in that value we just found, negative or positive 3, to the original equation. And we get 9 minus 18 plus 2, which is equal to negative 7. So the coordinates of the vertex are 3, negative 7. So I'm going to go ahead and plot that. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So all the way at the bottom there. And it says it wants us to find the vertex, the coordinates of the vertex, which we just did, and the coordinates of the x-intercepts. So to find the x-intercepts, let's let y equal 0 as usual. You always let y equal 0 to find the x-intercepts, and you let x equal 0 to find the y-intercepts. If we set y equal to 0 and try to solve this, we're going to find we can't do it very easily. We have to use the quadratic formula. So we try to factor, but if we can't factor, then we have to use the quadratic formula. So negative b plus or minus root b squared, and be sure to write it parentheses, minus 4 times a times c over 2 times a. Okay, so the x-intercepts are going to be positive 6 plus or minus root 36 minus 8. All this yellow part became negative 8. Let's double check that, make sure everything's correct. It all looks correct. 2 times 1 is 2. Okay, so 6 plus or minus root 28 over 2. 36 minus 8 is 28. And 28 is 4 times 7. 4 comes out as a 2. And then we have 3 plus or minus root 7. Because we're dividing 6 by 2, and we're dividing 2 root 7 by 2. Now, root 7 is between root 9 and root 4. Root 4 is 2, and root 9 is 3. So this is between 2 and 3, but it's closer to 3 than it is to 2. So I'm going to estimate that to be 2.7. So 3 plus 2.7 is 5.7. So one x-intercept should be approximately at 5.7. 1, 2, 3, 4, 5.7. Now again, we approximated this to be 2.7. So if we subtract from 3, we get 0.3, which would be about here. So we don't really have a lot of time to find any more points. So I'm just going to connect the dots. The graph should cross at 2, and it crosses right about at 2, so that's good. So this is the vertex, and these are the x-intercepts here and here, so we have the points drawn. But I'm going to write the x-intercepts up here, so 3 plus root 7, comma 0, that's one x-intercept, and 3 minus root 7, comma 0 is the other x-intercept. So I'm going to rectangle those, and I'm going to rectangle the coordinates of the vertex, because these are a part of our answers. And now we just have to find the equation of the directrix and draw the directrix on the graph. But it looks like the window is not big enough, so I'm going to come back with a bigger window. So I'm going to redraw this graph with a new grid. Sorry about that. Because we ran out of room for the directrix. So we've got our vertex here, and we need the directrix line. We can't find the directrix unless we find P first. So remember, P is always equal to 1 over 4a. Problem is, what is 4a? Or what is a, that is? A is obviously 1. We found that up there. So if a is 1, then P is 1 over 4. Now the equation of the directrix is always the value of the y value of the vertex minus P. So the y value of the vertex is -7, and P we just found is 1/4. So the equation of the directrix is -7 and 1/4. -7, 1 1/4, that would be approximately here. So we have the equation of the directrix. Let's rectangle that. And we have the directrix written on the graph, and the vertex, and we have exact expressions for the x-intercepts. And let's just go back over and make sure we found everything we were supposed to find. Looks like we did. So on to number 18. Go ahead and try number 18. When you come back, we'll do it together. Okay, we're back. Let's change f of x to y just to make it easier for us to work with that equation. Now that I look at this equation, I see that there's really not much we can do. There's not much that we need to do to change the form of the equation. So let's just proceed to use our transformation method to graph that. So the parent graph is going to have an asymptote. The parent graph is y is equal to 2 to the x. So there's a horizontal asymptote, if I can get the right thickness here. And you plug in 0, you get 1, you plug in 1, you get 2, you plug in 2, you get 4, and connect the dots. And the question is, should we reflect first or should we translate first? And the answer is we can do either. It doesn't really matter in this particular case because of the cumulative property of multiplication. I'm going to reflect first. That's not going to change the position of the asymptote. We're just going to reflect across the y-axis. And we get the following graph. And then we're going to dilate, so we're going to change the equation to y is equal to 2 to the negative 2x. We're multiplying x by 2, so all the x values are divided by 2. And that's not going to change the asymptote. So that x value becomes 1/2, this x value becomes 1. So it's a horizontal compression. We're pushing the graph inwards from the left and inwards from the right. We're pushing the graph towards the y-axis, that is. That's a horizontal compression. Okay, so that's our graph. Now we can find the domain in set notation by looking at the final graph. This is the graph of the function. So domain is the set of all x values. And now that I think about it, when you have set notation, and x can be anything because x goes to infinity to the left, infinity to the right, so there are no x values that cannot be plugged into this function. So the domain is all real numbers. Now the range is restricted because there are no points down here, which means that y, the range is the set of all y values such that y is greater than 0. This graph never touches the x-axis, so y is never going to be 0. So if you got that one right, good. Okay, on to number 19. Go ahead and try 19, and when you come back, we'll do it together. Okay, we're back. The nth root of a over b is equal to the nth root of a over the nth root of b. So we're going to use that principle here. And before we even continue, we should probably specify what exactly we're doing. Well, we have two problems. One is we have a perfect cube inside 72, so we're not allowed to keep perfect cubes inside a cube root. The second thing is we have the root over the denominator of this fraction, so we need to rationalize the denominator of the fraction. So we have two goals here that we need to accomplish. So now we're going to use the principle that the nth root of a times b is equal to the nth root of a times the nth root of b. Same principle, just now we're using multiplication rather than division. So in the denominator of the fraction, I'm going to change to, well, before I do that, let's factor. So that becomes 8 times 9 and x to the 6 times x squared. Now I could have factored in many different ways. Why did I choose to factor it like this? Well, because x to the 6 is a perfect cube and 8 is a perfect cube. I'm trying to pull out the perfect cubes from this expression in the denominator. So now we can use that principle I was telling you about. And so when you have a product inside a root, you can break it up into the product of a bunch of separate roots. And so the reason we did that is because this is a perfect, or this is a whole number. The green expressions are very easy to simplify. The cube root of 8 is 2. The cube root of 6 is x squared. And we can't do anything with the cube root of x squared. So those green expressions became 2 and x squared. Things are becoming simpler and simpler. So now we can collect the 2 and the x squared together, and we can put the 9 and the x squared back together. In fact, you really didn't have to separate the 9 and the x squared. We could have kept those in there. Okay, so now what we're going to do is we're going to multiply. And by the way, what we've accomplished at this point is we pulled out the perfect cubes. That was the whole point of what we just did. We pulled out those green numbers. But now what we're going to do is we're going to get rid of the root in the denominator. We have a root in the denominator. So I'm going to multiply both sides of the equation by 3 cube root 3x. Now, why in the world am I doing that? I'm doing that because when you multiply cube roots, you can just multiply what's inside, and 3 times 9 is 27. Why am I trying to make the number 27? Well, because that's a perfect cube. If we're cube rooting a perfect cube, then the cube is going to go away, or the cube root is going to go away, that is. X squared times x is x cubed. X cubed is a perfect cube. So again, the cube root is going to go away. So we need to multiply the numerator, and they're both cube roots, so we get cube root, and we multiply the 5 and the 3x to get 15x, and the denominator we get 2x squared, and then again we're multiplying the inside parts here because they're both cube roots. If one was a fourth root and the other was a cube root, this wouldn't work. They have to be the same. They have to have the same index. So 9 times 3 is 27, and x squared times x is x cubed. And again, 27 and x cubed are both perfect cubes. The numerator we can just rewrite. And the cube root of 27 is 3, and the cube root of x cubed is x. And the final answer is going to be the cube root of 15x over 6x cubed. So if you got that one right, perfect. Let's go back and double check that, make sure everything is right. Looks like everything is right. So go ahead and try number 20, and when you come back we'll do it together. Okay, we're back. So the problem is we have a root in the denominator of the fraction. So we want to rationalize and simplify if we can. So I'm going to use a math trick. This is a very tricky thing that I'm about to do here. I'm going to multiply both sides by root 6 minus 2. Because in the denominator we have root 6 plus 2. And we're doing this for a reason. It's going to get rid of the roots in the denominator, or this root here specifically. So in the numerator, let's use FOIL. Root 2 times root 6 is root 12. Those are both square roots, so you can just multiply what's inside. Root 2 times negative 2 is negative 2 root 2. And negative 1 times root 6 is negative root 6. And negative 1 times negative 2 is positive 2. Root 6 times root 6 is root 36. Root 6 times negative 2 is negative 2 root 6. And then 2 times root 6. Whoops, sorry. 2 times root 6 is 2 root 6. And 2 times negative 2 is negative 4. That's FOIL. So we can pull out a perfect square here. 12 is 4 times 3. 4 is a perfect square, so that comes out as a 2. The 4 comes out as a 2. And root 36, that is 6. And these inside parts, they cancel out. And our final answer is going to be 2 root 3 minus 2 root 2 minus root 6 plus 2 all over 2. Now, I know what you're thinking. You're thinking, well, wait a second, can't we divide all of these by 2 and cancel out these 2's? This 2 would turn into a 1. We could do that, but the problem is this purple coefficient here. There's no 2 there. So we could divide and cancel out the orange 2's, but we'd be left with a purple fraction. So you could do that if you want to, but I'm just going to leave it in this form. And what we accomplished there is we got rid of the root in the denominator. So if you got that answer, good job. Go ahead and try number 21, and when you come back, we'll do it together. All right, we're back. So we need to solve by completing the square. So the first thing we need to do is to divide both sides by 3. Then we're going to put the 10 over 3 on the other side of the equation. Then we're going to complete the square. Those are the same steps that you always use for completing the square when you're solving a quadratic. So we're going to look at this special number here, and we're going to do two things. We're going to divide it by 2 and square it. If you divide by 2 and square it, you get 1. And we're going to add 1 here to complete the square. But you can't just add 1 to one side of an equation. If you add it to one side, you have to add it to the other side. So the reason we did that is this square is now completed, which means that we can factor to x minus 1 times x minus 1. It's called a perfect square because these two factors are the same. What two numbers multiply to 1 and add up to negative 2? The answer is negative 1 and negative 1. Negative 1 times negative 1 is positive 1. Negative 1 plus negative 1 is negative 2. So we can write those factors in condensed exponent form. And the reason that we did all that stuff is because now we just have one x, whereas up here we had an x squared and an x, which was much more complicated. So now we're going to try to isolate x, whereas we couldn't before. But we can't do that because there's a square here. So we have to square root both sides to get rid of that 2 power. And probably the biggest mistake that students make when they square root both sides of an equation is they forget to write that plus or minus symbol. So just be aware of that. Now we have to rationalize the denominator here. So I'm going to multiply both sides of that fraction by root 3. And we get root 39 over 3. Now, if you want to go back and review how to do that, if you're confused, go ahead, but we don't really have enough time to show every step of that. So I'm going to add 1 to both sides, and we get 1 plus or minus root 39 over 3. Those are the answers. So there's 2 answers to that problem. And you don't have to worry about extraneous solutions because we don't have any logarithms or anything weird like that. So go ahead and try number 22. And when you come back, we'll do it together. All right, we're back. So we're going to convert to intercept form and vertex form. This is standard form. So first I'm going to convert to intercept form. I'm going to factor out -1. Then I'm going to factor. So what two numbers multiply to -4? Two numbers multiply to -4, but they add to -3. And the answer is -4 and +1. So this is intercept form. Now we're going to convert to vertex form. So be aware that probably the easiest way to do that is to understand we already have this a value. So we just need to find the coordinates of the vertex. Probably the easiest way to do it is Vx is equal to m plus n over 2 when you're in intercept forms. So we already have those two numbers. And so we end up with 3 over 2 for the x value of the vertex. Now this is kind of a pain because we have to now plug in a fraction back to here to get the y value of the vertex. That's kind of painful, I know. But sometimes you have to deal with fractions. I can't protect you for your whole math education from fractions. You just have to get used to using those. So we're going to plug it in, bite the bullet. 3/2 times 3 plus 4. And let's do the math here. So we get -9 over 4 plus 9 over 2 plus 4. And that's -9 over 4 plus 18 over 4 plus 16 over 4. -9 plus 18 is 9, and 9 plus 16 is 25. So now we're ready to write the vertex form because we have A. A is -1. So y is equal to -1 times x minus the x value of the vertex, which we found is 3/2, plus the y value of the vertex, which is 25 over 4. So that is vertex form. Now we could try to complete the square. That would also work, but that would probably take longer. Okay, on to 23. Go ahead and try 23. When you come back, we'll do it together. Okay, we're back. So I'm going to change f of x to y, just to make it easier for us to change the form of this equation. Then I'm going to add 2 to both sides of the equation. Then I'm going to divide both sides by -2. And you can keep the negative in front of the y plus 2, or you can distribute. It just depends on what you want to do. I'm going to distribute just to show you what it looks like when you try some different methods here. Okay, so let's go ahead and get started here with our transformations. We have a lot of transformations to do. So the parent function is obviously the reciprocal function, and of course there are there's a vertical asymptote and a horizontal asymptote, and we have our 6 reference points. I don't need to go over those for you because you've seen them plenty of times. So we have our parent graph. And now we need to be very careful about the transformations that we perform. Should we, in this form, and it depends on what form your equation is in. If you did not distribute the negative up here, then you're going to do it in a different order. You're going to dilate first, then you're going to translate, then you're going to reflect. You must do it in that order. But in this form here that we have, you're going to translate, you're going to dilate first. So let's go ahead and do that. So we're dividing y by 2. And so it's the same first step. That's not going to change the position of the asymptotes. We're just going to multiply all y values by 2. And now we're going to translate. So we're going to move the asymptotes 2 units to the right and 2 units up. And then, of course, we're going to reflect. So we're going to write a negative on y. The only difference is now y has a negative symbol in front of it. So what that does is it reflects across the x-axis. So we're actually going to change the position of the asymptote. At least the vertical position is going to change. The horizontal position is not going to change on that vertical asymptote. And so we have our point here. This point does not change positions. We have a point here. And we have a point here and here. So we just need to connect the dots, and we've got our graph. So that was kind of involved. We had to do a lot of graphing there. So looks like our graph is correct. Now we need to write the domain in interval notation. There's only one x value that cannot be plugged into the function, and that is 2. So the x values can be anything from negative infinity to 2, or from 2 to infinity, but we don't include 2, which means we need parentheses here instead of brackets. And the range is actually the exact same thing, except the only value the range cannot be is negative 2. Okay, so on to the next problem. So go ahead and try the first part of 24. When you come back, we'll do it together. Okay, so the future amount is equal to the initial investment times 1 plus the interest rate in decimal form divided by the number of times compounded per year to the number of times compounded per year times the amount of time that the investment is there, power. And we know after 3 years the investment grows to $10,344. We don't know the original investment, that's what we're looking for. We know the interest rate in decimal form is 0.02, and we compound biannually, which means 2 times per year. And this investment has been in existence for 3 years. So now we just have to solve for P. 0.02 divided by 2 is 0.01. 1 plus 0.01 is 1.01. 2 times 3 is 6. And 1.01 to the 6th power, be sure that you enter that into your calculator properly. If you enter it into your calculator properly, you should get approximately 1.06152, and on and on and on. I would keep that number into your calculator and then divide by 10,344 equals, but I divided the wrong way, so I have to push the 1 over x button in my calculator to flip that around. So the initial investment is, make sure you write a dollar sign. If you don't write a dollar sign, you're going to lose points. $9,744.52. So if you got that one right, perfect. Okay, go ahead and try part 2 of 24, and when you come back, we'll do it together. Okay, we're back. The amount of money that investment is worth is equal to the initial investment times e to the decimal form of the percent, the annual interest rate, times t power, t being the amount of time that the investment's in progressing. So the investment grows to $12,366, and the initial investment was $8,000. And we're looking for the interest rate, and it was invested for 20 years. So now we divide both sides of the equation by 8,000. 12,366 divided by 8,000 is 1.54575. And now we're stuck. We can't do anything unless we know how to use the calculator to find that exponent. That exponent is equal to log base e of that number. Now remember, log base e in the calculator is just ln. So in the calculator, you're going to use ln. So ln of that number is approximately 0.4355. Divide both sides by 20, and r is approximately equal to 0.0217, and it doesn't really tell us what to round off to, but our final answer is going to be approximately 2.17%. I guess I'll round it off to 2.18%. Again, the problem doesn't tell us what to round off to, so that's good enough. All right, so if you got that answer, perfect, good job. Now we just have one more problem and we'll be done with this practice test. Go ahead and try number 25, and when you come back, we'll do it together. Okay, we're back. So we need to define variables. Q is obviously going to be the number of quarters, and N is going to be obviously the number of nickels. And you might be thinking to yourself, do I really have to write that? And the answer is yes, you have to write it. Not only for your teacher, but also for you, so you know what these letters stand for. Okay, so we know that the number of quarters plus the number of nickels plus the number of dimes is equal to 38. That's this information here. we know that the number of nickels and the number of dimes, or the difference between them, the difference between the number of nickels and the number of dimes is 4. We also know that the total value of the coins is $5.90. So 0.25 times the number of quarters plus 0.05 times the number of nickels plus 0.1 times the number of dimes is equal to $5.90. So this is a system of equations. So this is a little different than we're used to, because normally in these problems we have to use the substitution method, or we don't have to, but it's easier to use the substitution method because one of the variables is solved for. One of the letters is by itself on one side of the equation. Well, that's not the case here. So we're actually going to use elimination. And the good news is that Q is already eliminated in this equation. So all we have to do is take the orange and purple equations and eliminate Q, and we're going to be on our way. So let's take the first equation and multiply by 2. So that gives us, actually we're going to multiply by 0.25. So that gives us 0.25 Q plus 0.25 N plus 0.25 D. And don't be afraid to use your calculator. 0.25 times 38 is equal to 9.5. You can do it in your head if you want to, but you're not required to do that. Okay, so we have that equation there, and then we're going to take the purple equation and rewrite it down here. So we have 0.25Q plus 0.05N plus 0.1D is equal to 5.90. Okay, so now we're going to subtract and maybe we should make this make it clear that this is a system of equations. So I'm going to make a brace there. We're going to subtract the bottom equation from the top equation, which is going to eliminate these Q's. 0.25 minus 0.05 is 0.2, and 0.1 minus or 0.25 minus 0.1 is 0.15. And 9.5 minus 5.9 is 3.6. Now you can use a calculator for that stuff. That's perfectly fine. So now we have the yellow equation, and we have this equation that we just made. So 0.2n plus 0.15d is equal to 3.6. And we have n minus d is equal to 4. That's that yellow equation up there. So if you don't have colors, you don't have to use colors. If you don't have colors, you can just use arrows. So at this point, we want to use elimination again. So we're going to multiply the yellow equation by 0.2. So times 0.2, and we get 0.2n plus 0.15d is equal to 3.6. and 0.2n minus 0.2d is equal to 0.8. So what that allows us to do is now subtract the equation, the bottom equation from the top equation, and these cancel out obviously, and this is a negative, so when you subtract it becomes positive, and we get 0.35d is equal to 2.8. So 2.8 divided by 0.35 is 8. So the number of dimes is 8. So that is one of our answers. Now, I know what you're thinking. You're thinking that was horrible. That was really, really difficult. But the hard part is over. Now that we have the number of dimes, we can use this yellow equation to help us find the number of nickels. So let me move this over a little bit. So let's use that yellow equation. The number of nickels minus the number of dimes, which is 8, is equal to 4. So the number of nickels must be equal to 12. So you see how fast we found the number of nickels. Now we can use that orange equation. The number of quarters plus the number of nickels, which we've just found is 12, plus the number of dimes, which we found is 8, is equal to 38. That's the orange equation. So now just doing basic algebra, we have q plus 20 is equal to 38. Subtract 20 from both sides. The number of quarters is equal to 18. So there you go. If you got that answer, good job. So that was the class today. If you'd like to take screenshots of all the work that we just did on this practice test to help you do your practice test for homework, go ahead and take screenshots. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5 and number 6 and number 7 and number 8 and number 9 and number 10. But don't go before you get your homework. The homework is another practice test. Here's screenshot number 1 of the practice test for homework. And screenshot number 2. And screenshot number 3. And number 4. And number 5. And number 6. Number 7. Number 8. Number 9. And number 10. But don't go before you get the answers. Remember, it's not enough to just attempt the practice test. You need to do it correctly. So make sure you get all the right answers. Here's screenshot number 1 of the answers. And here's screenshot number 2. So get that practice test done completely, correctly, neatly, and keep it in order in your binder. Doing this practice test for homework, as well as the practice test that we just finished, is the absolute minimum that you need to prepare for the final test. Do not take the final test unless you first take these practice tests. And remember, if you want to get a really good score on the final test, to prove to everyone that you actually know something, then you need to study everything, all the variations of the problems that we did throughout this entire course. And you can go back to the videos and click on the class work time code link, whatever you want to call it, and that'll take you to the screenshots of the class work. So get that practice test done, and I'll look forward to seeing you in the next class.